How can you change volume?
There used to be a way.
Sometimes it's okay, sometimes it's not. So you can figure it out how it happens. Maybe something happens when you restart it or something. I don't know.
I don't know. My computer has volume control somewhere.
You have here too, but I don't think it's
happened
from
a
here.
small triangle next to battery. Here.
Let's show hidden icons.
Yes. This is so volume.
Speakers.
There should also a microphone speaker. You tap there. No, there's
Alright, never mind. That's as good as it gets. Okay. Last time we considered the oscillation of warm electrons in an electric field that was assumed to be a plane wave. It's easy to calculate the velocity perturbation, and it's easy to calculate the rate at which it absorbs energy. It's just delta V times the force, and the rate at which it absorbs energy is equal to a non-resonant part which oscillates, and a resonant part. Now, there's a factor of I. Missing here. There's something here that's not correct. The UDT had a 1 over I in here. So this part should be real and this part should be imaginary. I see. This is the typo. This should be an I think. So this part depends on the sign of df dv. If it's positive, then particles lose energy on the average, and if it's negative, then the particles gain energy from the wave, which is what you expect thermodynamically. When this is positive, you have more particles at high energy than low energy. Now notice what I did here is I calculated the energy absorbed by assuming an F1, a perturbed distribution to the wave function, and F1 was given by this. Okay. Yeah.
Yeah. This M here and this K here, which one is supposed to be the other one for the units to be the same? I mean, one of them is a typo.
Well, first of all, this is hopeless.
Should be omega gamma small.
I don't know. This should be omega real, okay? and this should be omega sub real, not gamma. And this MK looks alright.
Maybe this is also V over K instead of V over M.
Well,
I don't see why we're going to get another
is
M.
I guess we're gonna have to go through it carefully. Okay, delta V is definitely this. This should be a dot, right? Maybe dot V. And this should also be a dot. Boy, she typed everything. Oh, here she got it right. Okay, UV dot V.
You should didn't notice the difference in the units.
I think it's fair to say you didn't proofread this last 2 years ago.
This one probably I did. I don't remember really correcting this part.
Okay.
But you went through this in lecture. That's when you were giving lecture last time.
Yes.
So I
So,
don't remember you correcting
you
it
know,
either. So maybe you just missed it completely today.
well, I try not. I mean, the whole point of writing these beforehand is so the students can go over it, and I don't have to get hung up on every detail.
I think I didn't understand this process because then I didn't go through this.
No, it's all that.
Okay.
Incorrectly.
No.
All right. It's EV dot V times F of V. These two lines I believe. You believe them?
Yes.
Because F is just F0 plus F1. You believe this? F1 is minus delta V times dF not dV?
Yeah, that's what you wrote as definition.
What?
Previously you defined F1 as like this.
Yes. Okay, so so we have and V is well, V is just a variable of integration here, and the idea is that yeah.
You define number density as F naught, and naught was F naught dV integral.
Okay, right. Let's go through this term in detail. V is odd in V, and F naught is even in V. So this F naught is gonna disappear, just because it's assumed to be symmetric about V equals 0. So that leaves us with this. So now we're up to the third line. You should by now start to believe the third line. Now F1 is delta V times dF naught dV, so the delta maybe should be out here, but since E and delta V are in the same direction, I don't think it matters too much. We know what delta V is in terms of E, so E times delta V is basically little e squared big E squared divided by M. And this this looks okay. This is just the velocity times df naught dv. And the k delta v definitely had a 1 over kv minus omega r in it. And actually, I could just write omega here. I don't have to write omega r. Because the reason I wrote omega r is because we separated out the real part and the imaginary part of omega. And we ignore the imaginary part when omega real is far from the resonant value kv. I mean when v is far from the resonant value omega r over k. So but basically I'm just replacing the delta v here with e squared over m times this denominator. So there's an m and there's a k. So are we okay up to here?
Mm-hmm.
Okay. This is the Flamelli formula.
You divide by v, so you took k out.
This is just a formula.
I took k out.
Okay, so basically your epsilon is epsilon prime, let's say, epsilon over k.
Alright, epsilon of k. Yeah, epsilon of k, but epsilon is just...
Small anyway.
Yeah.
This is just a formula, no units.
This is
you have units.
yeah, here you have units, here you don't have units.
It's just a formula.
So here I have to worry that this is why I divided by k, because I wanted x to correspond to v. So clearly what corresponds to k here actually corresponds to omega real over k here. So
You need to take the plus
well, I'm not even going to worry about the sign just yet. Now, there's certainly one value of m here. Now the point is this v is evaluated at omega r over k. In other words, this v here is part of the expression, right? Because there was a delta function that picked out this value. And of course this also is evaluated at omega over k. Now, there's no m here, and there will be a k, just like there was here. And the
Oh, yeah,
dimension,
yeah.
the dimensions look the same because v times df dv, and then dv over v is dimensionless.
Because you took a k outside, so you have to have a k also there.
No, I do, because this v is
No, but
omega.
you still have a v over there. You still need to divide by k.
That's true. Okay. Okay. The non-resonant part. If I were to consider the real part of E only, this would have a cosine times sine term in the E squared. Well, actually it does. And so its time average is 0.
Why?
And
The
spatial
real
average
part
is
is
0.
cosine.
Times sine? I
No.
didn't understand.
Sine is
Well, delta v E times
okay.
E
Yeah, it's sine cosine. Okay.
is when it's non-resonant, and it's because, and it's always that way. V is always out of phase with the force when it's out of resonance. And wait. Alright, if I use df dv, okay, look, I actually did end up with a k squared here. Anyway, why don't we check to make sure this has units of power density, which is what it is. This should have units of 1 over time, right? Because this is energy density, and this is plasma frequency squared. So
this is not the electric. This is energy density. Yeah.
So this is the plasma frequency. Now I'm dividing V by V thermal. I'm also dividing this dV by V thermal. So this looks right. And this is a dimensionless number.
So everything there dimensionless.
No, but
No.
omega p squared, I still have
1 over time by 1
over k.
No, it doesn't.
Okay,
That's the
alright, the point is the dimensions of f. When I integrate f normalized over v,
There's 1 over v.
so f has units of 1 over v, and if I multiply this v by, and actually it's of order 1 over v thermal, so if I multiply this k by f, that cancels out 1 plasma frequency, and it checks. It's 1 over time.
But you still need to have times volume, because
What?
U is energy density, or
Yeah,
energy?
but the E squared is energy density
No,
also.
but U is energy density, or?
Yeah, it's energy density, because F was normalized to density of particles. So you should So as I said before, if this is positive, the particles lose energy to the wave right around the resonance, and if it's negative, they gain energy. In other words, this is a classical. So the brightness temperature is essentially very high, so it's going to flatten out the distribution at the resonant frequency. If F is going down and this is the resonant frequency, so then it flattens it. It accelerates particles from just below to just above. Okay. Well, no. Yeah. I don't want to. Now, all this is when we threw away initial conditions. If initial conditions are preserved, then you can have waves that don't damp. And I think they're called BGK waves, Bernstein, Green, Kruskal. And it's a whole other thing. It's a nonlinear wave that just propagates. But the catch is, yeah, there's no damping. It's an exact solution to the Vlasov equation. And it includes particle trapping, but it's...
Is it like solitone?
Yeah, I think so. But,
what do you mean by no initial conditions?
No, the initial conditions in that solution are preserved. In the BGK waves, the initial conditions are preserved.
It never changes.
It means that I don't play this game of giving omega an imaginary part, so the initial so the conditions at minus infinity go away. Okay, so now the Vlasov equation is something that everybody should know, and this is just Liouville's equation, I guess, or something. This is just an equation in phase space, and here again.
That's a Vlasov equation. Yeah.
Well, if I put for the acceleration, if I put E over m.
Yeah.
For the acceleration, then it'll be the Vlasov equation. And if there's a magnetic field, I have to put E over m times E plus V over C cross B.
Okay.
And that'll be the Vlasov equation. For now, I'm neglecting the magnetic field. And again, F is equal to plus F1, and you solve for F1. And actually, this is just what I did before. It's just I calculated delta V. And here I'm just calculating delta V, delta T. But it's the same thing. But here you get to replace these derivatives with this e to the I kx minus omega t dependence. So dft plus v df is just omega minus I omega minus kv, and that's this. Now, when omega is small, there's positive imaginary pi, and yeah, we did this last time. So
F
let's
naught
skip
term
past.
over 0, that means a stationary solution.
What?
You're assuming steady state when you know the Laplace equation.
No, I wasn't assuming studies. I was assuming e to the I omega t dependent.
Okay.
And that's the assumption that throws away initial conditions. Assuming the imaginary part of omega is either 0 or positive, 0 or negative. So it's growing, which means that at minus infinity the initial conditions are just 0. And I could do it another way, where you actually see the initial conditions disappearing, and I'll do that later on in the course. So you could see that you're really forgetting information. You're not just setting it equal to 0, even if it was non-zero and you forget it, because of random processes gets wiped out, you still get the same result.
Okay, F naught is just background.
Okay. So I'm going to skip ahead. And now you should understand the basic wave-particle instability at this point. Okay, at this point I'm going to move on to say a few words about quasi-linear theory. Please be here. And it's a very nice discussion you can download off the internet. But basically, I'll just rewrite the Vlasov equation. Sometimes it's written like this. How does that happen?
What?
Just suddenly jumps off the page. Okay, now here's the key thing about quasi-linear theory. It's quasi-linear in the sense that you're expanding in F. It's linear in the sense that you're expanding linearly in F. The reason it's quasi-linear is because you're keeping track of the change in F0 caused by F1. So now I just plug back into the Vlasov equation, and what do I have? I have if I would have written it this way, Okay, so the point is that delta F is proportional, has e to the minus I omega t dependence. So the average value, its value averaged over time and space is 0. Again, I'm average. This means averaged over time and space.
Why is it 0?
Because this was the average of f over time and space, and delta f is whatever has an average value of 0.
At any given point.
Yeah, delta f is defined at any given point, but it's defined to be f minus the average value of f, where the average value means time and space average. So that means that if I take the time or space average of delta f, it's going to be 0. And not only that, but I'm assuming that the original f is homogeneous, so it's going to have 0 spatial derivative.
First you have to assume there is homogeneous, then is it implied that delta f average?
Yes, I'm assuming it's homogeneous.
And then it's implied
but
that
F0
yes.
doesn't solve the Lasson's equation.
I never said it did. I never said it did. But you agree I can erase these terms?
So why is it F0?
What?
So why is it F0? F0 means that it solves the Lasson's equation, right?
No. F0 does not mean it solves the Vlasov equation. This is...
So why taking this as F0? I don't understand.
What?
So why taking this as F0? I don't understand.
I'm defining F0 to be the time and space average of F.
Okay.
Like if it's a Maxwellian with uniform density, that's, or something, any function of purely a velocity. So, oh, and here I made a mistake. Here I should have taken...
Why?
In fact, I should have taken... The average, when you have an equation, you have to take a time average. Everything is... The bracket should be outside. Okay.
I mean, you should take average over F, no? Yeah.
Okay, I should also say that we're talking now on time scales that are much longer than omega. So the e to the I omega t canceled out, made everything 0 on short scales. But on long scales, I can have a slow evolution of f. So that's why I'm going to write it out. If I put the brackets outside the time derivative, it would be the same thing. It would refer to the slow evolution. And this, I think, totally vanishes. So what do we have now? We have QE okay, that's the delta F term, and we also have QE over M of
Why? Yeah, that's true, but where is the derivative of it?
sorry. Okay, now the point is
The other one also.
You're assuming homogeneous electric field.
No, I'm assuming e to the I kx minus omega t, dependence of the electric field. Which is why when I take the average space or time or fast time average of this term, it'll also go to 0. Right? Because when I average e to the I kx minus omega t over space or time, it goes to 0. Now here, delta F is a function of V, but since I'm averaging over space and time, I can take this V out. Okay.
Can you write maybe a small notation that we know is over space and time? Below the bracket maybe say T.
Yes, T.
So we just remember when we read that.
I'm going to write fast time. And or space. Now here's the thing, E and delta F, even if I assume e to the I kx minus omega t dependence, they can still have a spatial average because the phase of F correlates with the electric field.
Delta F has no dependency of T and over time and space.
Yes, it does.
You said
No, I didn't. I never said that. I said the unperturbed part of F has no dependence in time or space. The perturbed part does.
So why did we throw the d delta F to dt? The average of it?
Which term did we throw out?
The d delta F dt.
Because it's,
Yeah, but
first of all, there was no E here. This
yeah.
just had e to the I omega.
Yeah, I agree.
But this has E, which has, by itself, has zero average, and this has zero average, but when you multiply them together and you take the average, it's not necessarily zero. Okay. So, we get this. Now, what did we have for delta F? Well, for a given value of k, we had delta F was equal to minus I times Q over M EK dF dV omega minus kV. So now we can write dF dt is equal to d dV dF dV here and let's just put a K here for consistency. And we finally want to sum over K, because E squared is the sum over K of E sub K squared. Yeah, I mean, until now, until now there was E times delta F, and delta F also had an E in it. But, you know, I could have written this as follows. I could have written E times the sum over K. No. I could have made a Fourier composition at this point. I could have made the Fourier decomposition here. I could have written E as the sum. I could have written E as the sum of EK, e to the I k minus omega kt. Omega is a function of k. And when I did delta F, I could have written as the sum over k prime of e k prime over m e to the I k prime x minus omega k prime t. When I multiply these together, I would have a sum over k and over k prime. But when k didn't equal k prime, once I took the average, they would go away. So the only terms that survive the sum over k and k prime is when k equals k minus, well, k equals minus k prime basically, but
you have there omega minus k delta f equals k prime, sum over k prime.
Where?
Unity divided by omega minus k v.
Yeah, right. Okay. So now I write this. Look how I write this. I write d dv d dv of f times d of v. And this is nothing other than the diffusion equation.
If you have this factor of omega minus kv in the denominator,
What?
the factor of omega minus kv is in the denominator.
Right.
Even then the argument is valid, the k must be equal to minus k prime. Or maybe derivative, I think certain derivative.
Well, no, I mean the e to the I k minus k prime x.
That gives you delta function if you integrate over x.
It's a delta function, which means when k is not equal to k prime, it vanishes.
So since you have k in the denominator, so it's not really delta function.
Yeah, he's
The
right.
derivative is delta function.
It still vanishes when k is not k prime.
Yeah, but I think you have to take a derivative to get rid of k in the denominator. And it's simply
I'm not following.
it's not delta function if you have k in the denominator, right?
I'm assuming a discrete number of nodes
Okay.
when I do that sum, and there's just going to be terms where k equals k prime and k doesn't equal k prime. I'm keeping the denominator just as it is. What did I just do?
That one more time.
D um
No, he's right. It's k equals k prime.
who's he? Me or Rahul?
You still need to have k when k is not equal to k prime. It's 0 because you have a delta over v minus I k and not k prime.
That might
It may be the
turn out to
derivative
be-
of delta function, but I'm not writing delta functions here. I'm just writing sum over
No,
node.
it's okay. Just factor something.
It just stays omega minus kv.
Yeah, anyway, derivative of delta function.
Anyway, I wrote omega here as the real part plus I gamma. And now, if I wanted, now I could decompose this into a principal value and a resonant part. Now here's the thing. I think this is right. The question always comes up, though. What would happen if at a certain velocity the resonant wave, there were no resonant waves at all? So then I would have some value for here, for this. Because the the denominator is finite even when this is non-zero. But in general, this is going to have a real and an imaginary part. And since this equation is obviously an equation, for a real function and a real diffusion coefficient, you throw away the imaginary part, because some of that delta V, non-resonant delta V, is reversible. I mean, remember where all this D came from? It came from a correlation. It came from a correlation between the electric field and the perturbed function. Now, they are for non-resonant particles, they are correlated. It's just that they're out of phase by I, by pi over 2, which means that if I kept the true complex value of e to the I kx minus omega t, it would be rotating around in phase, right? And the electric field and the velocity would always be 90 degrees out of phase. So there would be a time average value there, but it would be imaginary. And what's really happening is that I have a potential. You know, the electric field is positive here, and negative here. This is the potential of X, and particles are oscillating back and forth in this wave. So it passes a point, it's going to be going up, and it's going to be coming down. So even though the velocity and the electric field are formally correlated in phase, there's no net irreversible change in energy for the particles. Because when they were going up, they were being pushed one way, and when they were coming down, they were being pushed the other way. In one case, they lost energy. In another case, they gained energy. And if I had taken the spatial average, in any case, the imaginary part of the diffusion coefficient would vanish. So, for example, in these notes, they right from the start say that it's the real part of this expression. And they kind of sneak the real part in here. But I've explained physically why they do it. And I remember learning this in graduate school. The professor didn't quite know how to say it. He said the sloshing back and forth it looks like velocity diffusion because there's a delta V and there's a delta T, but it's not real. And the real part is due to the resonance. So when you have a distribution function f, and you have a wave spectrum, so you get diffusion, you get flattening due to resonant wave particle interaction. Here you get, the non-resonant part would give you short-term fluctuations, maybe. It's like you're getting an imaginary part of the time average value of f, but you throw it away. Okay, so that's the that's quasi-linear diffusion, and it's a useful concept to know. Now, to go on, the next thing I want to do is derive that same diffusion coefficient, but from the point of view of the particle, not using the Vlasov equation. And we'll see the short time scale and the long time scale in a slightly different manner. Now, I can pause this, right?
I think it's still recording.
Why?
I don't know.
Oh, because I tapped twice.
Yeah.
What I'm going to do now is rederive the diffusion coefficient from the point of view of the particles. Okay, delta. This is the energy This is an energy diffusion coefficient as opposed to velocity. So it'll be a little different, but not too bad. Instead of having just the force, I'm going to have the v dot the force. But the structure will be the same. And also, I'm going to include a magnetic field in here, so that you'll see how that works when there's Bessel function expansion. Because it gets a little messy when the particle's gyrating. It's not just e to the ikx. Then usually I don't do that, but since my notes weren't loaded somehow, I'm going to use recent notes from a paper I'm writing. Now the thing is, what you do is you write delta E squared as a product of two things that look different, but they're actually the same. T prime is a dummy variable, and T double prime is a dummy variable. So this is delta E, and this is also delta E. And together they make delta E squared. But now, instead of x just being Vt, dividing the motion up into motion along the magnetic field and motion perpendicular to the magnetic field. Now, when there's no gyro frequency, when there's no gyration, let's say either because there's no magnetic field or because the particle has no motion perpendicular to it, you can ignore these terms, and then this x naught plus v naught plus v parallel t is just what I would have written in my other notes, which aren't here. And what's extra here is just the terms proportional to x and y, which represents motion perpendicular to the magnetic field. Now, this describes an interaction of a particle with an MHD wave. In MHD, the electric field is equal to minus U cross B over C. That's what the electric field is. And here you're seeing in principle there can be electric field along Z, but in this context I think I'm going to ignore that. You already saw that for electrostatic waves. So now I'm going to do electromagnetic waves. And the type of resonance can be entirely different. Turn off your cell phone before you come in here. Read the sign on the door.
Yeah, I'm sorry, it's my Wi-Fi.
What?
It's my Wi-Fi.
You can't turn off. You're not allowed to turn off your cell phone.
Okay.
So I'm replacing U, the fluid velocity, times B cross B over C for the electric field, and I'm assuming it has K dot X is now a vector quantity that includes all these terms, displacement perpendicular to the magnetic field. Now when you replace this exponent with x of t, first of all, you're going to get this whole long expression for the velocity, and what I really have to do now is replace x with the orbital parameters of the particle, and we know what x is. It's equal to this. So I have to take this and replace it for this x in the exponent. Now I should. Can somebody enlarge this? Just yeah, I guess it's enough. Now the point is, you're going to get all these signs.
Is it still quadrilateral theory?
Yeah. it's going to come out equivalent to what we calculated before. Except here we're calculating it for a cyclotron resonance. If you just kept the electric field and just kept
Post-catastrophe.
what?
This is minimized.
Minimize
no,
this?
No, that's one note. This one here.
I don't want this. Oh, is this the lecture? Oh, yeah, okay. Whoops. Okay, if I had just kept this term here and this term here and let Rg equal to 0, and I just kept the electric field as, I just would have gotten something that looked like e to the I k v minus omega t prime times e to the I, just a second, this is also a t prime, t double prime. And when I did, and this is equal to basically e to the I kv and actually to get the real part of a square, I just take the complex conjugate the second time. So this is actually a minus sign, and then this becomes t prime minus t double prime minus t prime. Oh, let me write it this way. It becomes e to the I k v minus omega t double prime minus t prime, and the integral is over t double prime and t prime, but the integral depends only on t prime, only on the difference between the two. So that's a key point in this derivation, is that when I integrate this dt prime minus dt prime, I can write it as d t prime minus t prime over the square root of 2 times d t prime plus t double prime over the square root of 2. Okay? And now the integrand depends only on one variable and not on the other variable. So this ends up being approximately, and remember this integral is going from 0 to t. And the integral is going from 0 to t.
And the second one also 0 to t?
Yep. And the third one also 0 to t. So the integral from 0 to t of dt
Shouldn't be 2t or t.
No, no.
yeah, actually it should be 2t. But I'm gonna divide it by the square root of 2 squared. So, and then the integral from 0 to t, well,
No, this
No,
should
this
be
is from 0 to t.
yeah,
0 to
it's actually, it actually doesn't matter because you're going to assume now that t double prime minus t prime uh,
0 to t prime.
yeah, okay, but it doesn't matter because you would assume that whatever this is, it's much longer than the correlation of um, remember, I'm taking the ensemble average of this, and I should have made that clear. See, here there are brackets, and that means I'm going to assume that the correlation of the electric field between time t prime and t double prime doesn't last very long. At some point, the ensemble average makes it random, and therefore I assume that that this integrand, even though I didn't write the random phases, I should have written 2 random phases, which are also functions of t, and that the ensemble average of e to the I t double prime minus it has a short lifespan. In other words, it goes to 0. This is called the correlation time. And you assume the correlation time goes to 0. God, fucking son of a bitch, what just happened? I don't want this. How do we get back to where we were?
you tap electricity again.
On this?
Yeah, turns it up. I don't know what happened with this.
Yeah, I'll tap on this.
No.
Okay. You assume that this time is the correlation time is much less than t. So it does not matter what the value of t is here. I essentially set it equal to infinity. So now I have to do this integral. And that's another thing that I'm going to show you, which is worth learning, is studying how these phases decorrelate. and doing the integral exactly, and you'll see that you get something similar to what we got before. But remember, without this decorrelation, this integral would just be 1 over omega minus kv, like we saw before. But I specifically want to get there.
This is like turbulent electric field, right?
Yes, yeah.
And you are calculating E square after this, right?
Okay, now the other thing that you should be exposed to is this Bessel function identity. That when you have a trigonometric function in an exponent, it can be expressed as an expansion in Bessel functions. And you can prove this just by expanding the exponent in powers of sine phi. Phi here is just an angle. So so basically the expression for the power absorbed is just a infinite sum of Bessel functions, and you still have this e to the in phi where n is being summed. So this is like harmonics in the angle. Anyway, I used one more identity here, just a recursion relation for Bessel functions, so that when I had just because there was another cosine theta that appeared in the integrand next to the exponent. So when I expanded the exponential, I still had to multiply it by cosine of phi, and cosine, as you know, is e to the plus 1, e to the plus phi times e to the minus phi. So to this n it added a term of n plus 1 and an added term of n minus 1. But that's just the way I did it. If I had expanded the force, there would be no factor of cosine theta next to it, because that came from the velocity. But the point is that you can express the power absorbed as a infinite sum of Bessel functions, and
isn't the derivative in recursion relation of Bessel function?
what?
Is it Jn prime in the reduction side? I don't remember actually.
I don't understand.
Is it derivative of with respect to z? No, maybe I don't remember.
No, this is 1 over z.
Maybe that's different recursion.
That's different recursion relation. Anyway, when you go through the algebra, leaving aside the business about the phase randomization, you get a sum over Bessel function, but you get this still remaining in the exponent. This is the the value you would get without a magnetic field, without a zeroth order magnetic field. And this describes the cyclotron frequency of the particle. And notice that you're going to have terms with, you're going to have a term where n equals 0, and then the resonance condition is just k parallel v parallel equals omega, which is what we had before for the resonance. But suppose n is equal to 1, and suppose that the cyclotron frequency is much bigger than this frequency. Or to put it differently, k parallel v parallel minus omega is the frequency of the wave in the frame of that moves parallel along the magnetic field with the particle. And then you can have a cyclotron resonance, a cyclotron term. So you can have a resonance if this is equal to let me write it this way. The frequency in the frame of the wave is omega minus kV. If the wave just happens to be some multiple of the cyclotron frequency, then you also get a resonance. For when n equals 1, that's called a cyclotron resonance, and it's just that the particle is gyrating around and around, and the wave, the electric field of the wave, is gyrating around with it. So that also adds resonant energy to a particle, and the n equals 1 resonance is very important in astrophysics. So actually, it's good that I had an opportunity to show you it. And I'm not going to go through all the algebra. I mean, it's too much for this course. Usually, I don't even do this at all.
Why is it important?
It's important for when particles, especially cosmic rays, scatter off Alfvén waves. They generally do so with an n equals 1 resonance, because cosmic rays move at the speed of light along the magnetic field or close to it, and the Alfvén velocity is much less than that. You never have a velocity resonance with cosmic rays, but you do have a cyclotron resonance, and that's what causes them to scatter. That's why cosmic rays are confined to the galaxy and so forth. So that's the second. I think we're done for now. Next time we'll talk about the phase decorrelation a little bit, and that'll be, I think, what you need to know for this course in terms of quasi-linear theory. All right.